In this video, we're given a potential energy function for a Hooke's law spring. So in a sense, this is the simplest kind of potential energy function. It's just an upright parabola. I made a little graph of it down here, and it passes through the origin. And the point of this problem is that we're going to work with the relationship between force and the potential energy function. So in part A, I'm asked to compute the spring constant for the spring by writing the force as a function of position. So we have to remember the force as a function of position is given by the negative of the first derivative of the potential energy function. So I have the negative of the derivative of 0.5 x squared. We simply use the power rule on this. Bring down a factor of 2, subtract 1 from the exponent, and I get negative 1, just to emphasize the coefficient here, negative 1 times x. And then the problem actually asked for the spring constant, so we have to compare to Hooke's law. F equals negative kx for Hooke's law. The minus sign is there to indicate direction. And I compare it to what I just got, and k must be 1. So k is going to be 1 Newton per meter for this spring. In part B, I'm asked to show that x equals 0 is the location of a stable equilibrium by using the first and second derivatives of the potential energy function. And you may recall that the location of a stable equilibrium is anywhere we have a local minimum of a potential energy function. And I can see from the graph, this is definitely a local minimum. We just have to get into the derivative proofs real quick. So we're applying the first and second derivative tests here from calculus 1. And I want to find u prime of x. And I know that local minima and maxima should have a first derivative of 0 because I'm at the top of a hill or bottom of a valley. So u prime is given by, if I go back to my original function here, positive x. And then I evaluate that at the point of interest, which was x equals 0, and I get u prime of 0 is equal to 0. And we pass that first derivative test for a local minimum. Then we need to show that our second derivative is positive, and that will verify that we're at the bottom of a valley instead of the top of a hill. So u double prime in general is just 1, and that's a positive number. So to complete our explanation here, u double prime of 0 is 1, so it's greater than 0. And we pass the second derivative tests. And to be really complete, I'll say, therefore, x equals 0 is a local minimum of the potential energy function. And a local minimum gives us a stable equilibrium, meaning if we tweak the location a little bit to the right or left of that, the force will point back to the original equilibrium location, so we get oscillations around the stable equilibrium point. Just to emphasize what the forces are doing here, in part C, we're asked to verify this is a stable equilibrium by showing that the force is positive when x is negative. In other words, when the particle is over here to the left of my equilibrium point, the force should point to the right. And that brings the particle back through the equilibrium position. And when my particle is over here to the right of the equilibrium, I want to show that my force points to the left, again, bringing the particle back toward the equilibrium position. And we already found out the force function in general. It's just negative 1 times x or just negative x. So then we think about it. When x is less than 0, my force function is negative x. So if I take a negative number and put a minus sign in front of it, I get a positive number. And when x is greater than 0, well, f is the negative of a positive number then, so f is going to be less than 0. And that means it points to the left. So we've verified that if our particle is tweaked to the left of the equilibrium position, the force restores it to the right. If it's tweaked to the right of the equilibrium position, the force restores it to the left. So this is called a stable equilibrium because when a particle is in this neighborhood, it will always stay around that neighborhood. And that's it. If you enjoyed this video or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.